everybody. Thanks for joining today. My name is Kelly Korreck. I'm an astrophysicist at the Smithsonian Astrophysical Observatory in Cambridge, Massachusetts. And today I'm going to ask you to fly with me to the sun. And I'm going to talk to you about NASA's Parker Solar Probe, our mission to actually fly to the sun. So a little bit more about me is I am a rocket scientist. I built this telescope here that you see here that my cursor is moving on. That is the highest resolution telescope that has ever taken pictures of the sun in the extreme ultraviolet, or when it's around 1,000,000 degrees on the sun's atmosphere. That's out in the White Sands, New Mexico. This is me in the lab. I spend some time in the lab as well. This is inspecting the optic before it went into the telescope, and pointing out that there's a hole in it and it's actually supposed to be there. So that's good. I work for the Smithsonian, and so the Smithsonian has things like museums on the mall that has the ruby slippers from The Wizard of Oz, and the panda bears that you can watch on panda cams, but they also do a lot of research. And so I'm in the branch where we do the research and build things like these telescopes that take pictures of the sun. So that's a little bit about me. Now jumping into our main attraction, our sun. So this is, if you do a glancing view of the sun outside on a sunny day, this is what we've been used to seeing for all of history as humans have known it, looking up at the sky and being thankful for the warmth that the sun gives us. And even as early as the 1100s, folks had started seeing features on the sun. Now, we never looked directly into the sun without special glasses, and only around times of eclipses. Those are the only times we can safely view this, but there were, through smoky hazes, they were able to see these spots that were recorded here on the sun, the spot here and spot here, that marred the disk. And so there was these sunspots. So it wasn't this perfect warm ball that we see here on Earth. There seemed to actually have been some spots and some character to this, giving us clues that the sun was more complicated than what we thought. This is a Renaissance painting of astronomers viewing the eclipse. And so looking at when the moon goes in front of the sun, and you start to see what goes on just around the sun, or when you block out the middle, you see things coming off of it. And so even in the 15th century, we were able to see that there were things going on outside of the sun's ball. So again, looking at the sun during an eclipse, one of the only safe times that we can look at the sun directly, you start to see these large things flowing out and flowing away from the sun. So this got everyone interested in terms of how far does it go? How does it actually reach Earth? And the question is, yes, this wind that constantly blows off the sun does reach the Earth. So we actually interact with our star, not just with heat, but also with a wind that's constantly blowing. And then when we enter the space age, we were able to actually take pictures above the Earth's atmosphere, and we're able to see these eruptions. So this is a picture of the 1,000,000 degree atmosphere of the sun. It's very, very warm, and all of these active regions or bright spots are above those sunspots that we saw in the drawings from the 1100s. And these are things that interact with us. You saw there was a large explosion coming off down here, and that material is the equivalent in weight to 80 million school buses racing towards us at millions of miles an hour. So there's all this stuff that the sun has that it's constantly throwing off at us, up to 3 to 5 times a day during solar maximum, 3 to 5 times a week during solar minimum, when the sun is a little quieter. And so there's all these interactions that the sun has that we're very interested in studying. And another reason we're interested in studying is this is a star field. So we look up at the stars and we wonder what things are like. So studying our sun, which is our closest star, enables us to look at these other stars and know something about what they're like and about what life on other planets would look like when it's outside our solar system. So that's another reason that we study and we look at the sun. So our sun is great in terms of being able to provide us food. All the food on Earth is produced somehow by the sun, whether it's the sun directly growing plants or enabling these plants then to be fed to animals that we eat. So that's one of the reasons why we really need our sun and to understand it. It also gives us enjoyment, places to go like warm beaches when we can go on vacation and just to warm us outside. It also puts on these amazing shows. I don't know how many have actually seen the Northern Lights or the Southern Lights, but the aurora are a beautiful phenomenon and a clue into the fact that we have a magnetically active sun. And so these are beautiful sheaths that you see when there's magnetic activity, those winds and those ejections that come towards us, and they shake the Earth's magnetic field. And that shaking of the magnetic field and the propagation into our atmosphere to interact with the air in our atmosphere causes these beautiful lights that we can see in the Northern or Southern Lights. And again, these clues were those spots, the magnetic spots on the sun. And it blowed up, there's a little bit better picture, there's a structure there, and they're like magnets. They're like really, really strong kitchen magnets. The magnets you have on your fridge, they're much, much stronger than those, but those are the similar magnets that we're talking about in the sun. And again, we're looking at this image where we block out the center of the sun, so we make our own artificial eclipse to look at all of that material being thrown off at a pretty constant rate here. The sun is constantly blowing off that material. It's interacting. We're far away, but at the same time, this does go out to the Earth. Now, the Earth isn't this close, but I just wanted to show you this for size. This is just part of the sun, and this is one of the starts of those ejections, and that's the Earth. The Earth could fit well inside of one of those ejections. So we just get all those coronal mass ejections can completely overtake the Earth and affect us in so many different ways. So we just talked about a lot of reasons to go to the sun. First of all, we're explorers. We do explore things, and we want to go there to explore. The second is the practical matter of living with a star. And then there's some scientific curiosity that we need to solve here. So Parker Solar Probe, the mission that I've worked on for over a decade, was actually 60 years in the making, a little bit older than I am. And it was first thought of or written down as in the Simpson Committee report in 1958. And that's when they said we should go to every planet in the solar system as well as the sun in order to study it and really understand it. It also founded NASA. So NASA was founded over 60 years ago. So in our exploring and the fact that we're explorers, we've gone to Mercury, Venus, the Earth, obviously, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. But we haven't been to the sun before now. So this was really the first time that we as explorers went in towards the sun. Now, some of you might have used these in the past, is use a GPS to get someplace. And that's a very useful technology that we use. We also use our television, especially right now, lots of time spent with Netflix or Hulu or whatever else, watching TV. But all that could be interrupted by those space weather drivers that the sun creates. So those solar flares, when things get super bright on the sun in little positions, the equivalent of the energy used in the US for 180,000 years. In one of those little flares. So you could power your house for a long, long time with some of these solar flares. Then we have these coronal mass ejections. Again, those 80 million school buses coming at us at millions of miles an hour. And then we have solar energetic particles, which are particles of plasma or gas that come shooting at us, and that can interfere with electronics, could interfere with that GPS satellite that gives you your position to where you're going to school or work or your friend's house, and as well as the TV and other the electrical grid. So there's a lot of different effects of that space weather, and they're shown here in summary, having the sun in the center, and then things such as damaging those GPS satellites, possibly inducing issues with the electric grid, an effect on air traffic or airplanes. So it's really important to know this because we can mitigate this all. We're smart enough to know how to deal with it. We just need to know it's coming. We need to know how to predict it. And then we can deal with it. So another reason, again, to go to the sun is scientific curiosity. So the sun is mysterious, and it does at least two pretty weird things that we're still trying to figure out. So first of all, what I like to talk about is the Campfire effect. So I think we've all been near a campfire or a fireplace, and when you're close by, it's warm, and as you walk away, it gets a little cooler. However, the sun is very strange. At the center of it, where you get the heat source, that's its core, it's producing a lot of heat, and that's at 15 million degrees. As you go out from that, it gets gradually cooler until that outside ball you see is around 5,000. Well, however, you then walk away a little further and you get to the atmosphere of the sun, and that gets hotter than the surface at 1,000,000 degrees. So it's like walking away from a campfire and actually getting warmer. So that's something that we really want to understand and to take a look at with its mission. So again, this is a diagram of the sun if you were able to somehow slice it open like an orange, and looking at that core where it's much warmer. And then you go to the surface where again it's less warm, and then the atmosphere where you go to 1,000,000 degrees. So we have a couple of theories, and these are images taken from telescopes up in space of one of the theories that we think is there is movement of these magnetic fields, like you kind of see up here in this in the magnetic field dancing, and that motion causes heat, and that would cause it to be warmer. So we need to take measurements to understand the magnetic field and the temperature at the same time in order to see if that's right. Another way that we think that it could get heated is through these explosions. You'll see an explosion here, and is it here that we're actually heating all of the atmosphere up to 1,000,000 degrees? So we're going there to find out again. There's also all that wind that is constantly blowing off, as we see by this comet tail that's directed away from the sun. So the sun is here in this image, and that comet tail is always directed out. So there's always that flow outward. So we're trying to figure out how that happens and how the sun can lose that mass and still maintain its shape. So the mission design is to go from launch at Earth and go in and pass Venus, actually interact with her 7 times in order to push us further and further in. So doing a maneuver called a Venus gravity assist. So it's taking Venus, and when we get close to her, she moves us, and she pushes us in closer towards the sun every time we interact with her. So once we get there, once we do this, we made sure to take a thermometer, because that was one of the things that we wanted to look at. We took a wind, something to measure the wind, the speed and the direction. We took also a magnetometer in order to measure the magnetic field, as well as a camera, because on any good trip and any good explorers, you take some pictures and send them home. So this is the engineering schematic of what that spacecraft looks like. So the thing that measures the wind is up here, as well as there's two other sensors here. This is the high gain antenna. That's actually the phone to phone home. That's how the spacecraft talks to the deep space network, and that tells us in radio signals what's going on and gives us our data. This is how we cool. Part of how we cool the spacecraft is actually with water. So we have water cooled in this radiator that enables us to leave some of the heat behind, so it doesn't warm up any of the back of the spacecraft. And then we have a thermal protection shield, a shield up front that keeps us safe, as well as our solar panels, which enables us to have the power to operate. This is just a spacecraft rolled on its other side to show you the other instruments that we took, that those magnetic field measurements, or to measure the magnets, are out here. The WHISPER instrument is our camera. So it's our camera to send pictures home. This is another particle detector or gas detector. And then these are for those energetic particles that we need to measure. So the specific instrument team that I work on is the SWEEP suite. It's a tongue twister. It stands for Solar Wind's electrons, alphas, and protons. So that measures what basically makes up the solar wind, all gas. It measures all the different types of gases. And it's made up of this little cup, the bravest little cup that ever was, that sticks around the heat shield. So when we were deciding to go to the sun, we decided not to hide behind the heat shield, but that we needed to sample it directly. So we peeked this little buddy right around the heat shield. And then we have 2 other detectors in the back, just because the wind will come from different directions as we go closer and near to the sun. So we put 2 other instruments on the back. And that's what we've been measuring. And so what we try to measure is, again, how much is there, so how dense it is, so how much of it is packed into a little spot. We also look at the velocity, which is a speed and a direction of which way the particles are coming from. So looking from where they're coming from. And then also looking at the temperature to see how hot they are. So we count the number of particles that hit our detector, and the peak number of those, or how many we get, is the velocity. The density is when we add up how many we've seen, and the temperature is about the spread of how many we get. So we're able to measure that, and that's going to give us answers about why it's so hot, and whether that has to do with magnetic fields or speed or different things like that. So now on to our actual design for our little cup, our brave little cup that looks around the heat shield. So this cup the particles would go into this entrance right here. So go in here, a lot of electronics go back down here to be in a nice cool spot back here, which is around 60 degrees. So about room temperature back here, and this can get up to 1300 degrees. So all of that is actually relatively old, but the environment is brand new. That type of cup has been used, this Faraday cup has been used throughout the space age. It's on Voyager, there's many different versions of this cup, but now the environment is super new. So it's 400 times brighter. It's up to 300 degrees Fahrenheit or 1300 Celsius. And what we normally make stuff out of, we're just not able to. So normally we have things like coax cables, the same thing that comes from your TV to a cable box in regular space applications. We use regular kind of test facilities. We can use tests on the ground. We use aluminum, like cans and glue, but we can't use any of those. So for instance, we do use a lot of aluminum in our construction normally, like the aluminum cans you'd have in a soda. However, we can't use that because that would melt at these temperatures. So we had to figure out brand new materials in order to do this. So at the same time, we also had to fly a heater to the sun. So this is a very unique mission where this part will be so hot that we need to cool it down, and that's why it has these beautiful radiators coming off of it. But we also have a bunch of heaters down here in order to warm up the electronics, because once you're shaded from the sun that close in, there's no other heat source. There's no other way to get heat. So you're actually looking at deep space. So you're so cold in the back, and you're very hot when you're looking directly at the sun. And I think that's the biggest kind of conundrum that we faced, is that at closest approach to the sun, we have to actually turn our heaters on. There's the possibility that we will freeze when we're closest to the sun. So it's a very, very weird mission. And again, when we're closer to the Earth, we're very warm, or about room temperature. But when we go to the sun, it's really, really hot. So again, the thermal shields, there's a special coating on this so that it doesn't reflect light, so it doesn't get any other heat. So again, we're talking about no other heat back here on this side. If we turn, we have to have a radiator, but then we also have the heaters down there. So again, we couldn't use aluminum. So instead we used tungsten, molybdenum, niobium, titanium, and sapphire. So when I first started working on this cup, I was promised a cup that was going to be made out of diamonds, sapphires, and rubies. So this is why I signed up for this mission. And what happened was the diamonds were supposed to be used for these grids in here, but they were too brittle. So they decided that was not able to withstand the shaking, or that would take off on the rocket. So that had been changed. And then the rubies ended up being not a good enough insulator, and so we went to sapphire. So at least they're still sapphires. Unfortunately, the types of sapphires that they have are right here, these little rods, and there's actually a ring that you can't see in here of sapphire, but it's white sapphire, it's lab-grown sapphire, not the beautiful blues that we think of normally in jewelry stores. But there's sapphires for insulators, so very rare exotic materials that we had to figure out how to use in different ways. We also can't use epoxy. So we would normally glue things together. Yes, we glue things together for spaceflight. But for this, the epoxy would melt and we didn't want it melting. So instead they went and actually tied all of these wires together and twisted them together so that when they're exposed to this huge shaking that goes on when you're on the rocket leaving Earth, they don't shake out or they don't fall out. So they are all tied together, so they can't shake apart and they can't move. So you can see here too, they're all tied together instead. And those are very, very small screws that were all handmade by a company to make sure that they were all the right material and they're all the right size. So there's this was definitely a very handmade instrument. Safety wired. And so those coax cables that I was talking about, those things that you usually see coming out of your TV to your cable box can't be used because they would also melt. So instead, we fully customized a hard coax made out of rubidium and sapphire beads that kind of keep it from moving in there. So it was a very delicate process. And so this is one of those coax cables. Looks nothing like that what comes out of your TV. Very, very different. And these are what actually bring our data down. And this is what supplies the energy to the actual instrument. So this is like the power plug that you plug into a wall. And then this would be any type of message you'd get out of the cup. So in addition to building this, we also had to test it. So it had to make sure that it was going to work once it got there. And we couldn't find a place where you would test something that's this hot and that it would also be exposed to all the gases that we think that it's going to be exposed to. So one of our engineers had an amazing idea to use old IMAX film projectors, like the IMAX 3D that you go and see a movie on, and instead of spreading it out to the 5 stories that you normally watch a TV on, you invert it and you squish it down into a smaller dot so that you actually take 4 of these and you simulate the sun inside of this vessel. So inside of that little chamber, we put our cup and we focused all this light so that we had all the light that's very similar to that, what's coming from the sun close by into here, and we're able to test it. There's also a gun here that actually shoots the gas into the cup so that it could have a similar profile to what you might see at the sun. And then all this test equipment here also simulates the light from it, so that we knew that it would work when it was hot and there was light on it, and that would also still measure all the gas. And this is pictures of it as it was being shipped out the door. We use FedEx, however, it ends up in these very special containers that have gas blowing very pure gas on it, so that it stays not contaminated, so that nobody's hair or there's no dirt that gets in it, nothing like that. These are some of the engineers sending it off as it leaves in its own FedEx Custom Critical. It gets its own truck ride down to DC from Boston. This was then when we got it into the DC area, and we're just about to put it on the spacecraft. So that's myself, my colleague Tony, and Chris, who worked also on this project with me. And this is me and the spacecraft. This is before we put her on. This was during a magnetic swing test, which is a very scary thing. You pick it up, and to make sure that you don't have any, you can measure those magnetic fields we want to, and not the magnetic field of the spacecraft or anything that we sent. You pick up the spacecraft and you swing it back and forth to see if it has any intrinsic magnetic field. So you're taking something that cost about $1 billion and swinging it by ropes, kind of like you would on a playground. So this was one of those scary tests that we did. In addition, we got to go to some really cool places to test it. So this is in Goddard Space Flight Center in Greenbelt, Maryland, and they have a several story tall vacuum chamber. So they basically suck out all the air, much like deep space, and simulates deep space. Not right now, obviously. There's the top off, and there's people in there, so we don't suck out all the air now. But when this is closed, it can simulate space. And so they dropped this, they did not drop, they placed the spacecraft in the vacuum chamber. And were able to do tests and with the whole spacecraft to make sure that I was ready for space. This is a cool test that turned it purple. These were testing each solar array panel to make sure that they were getting the right amount of energy. They know how much energy is coming out of here, they know how much energy is going into here, and then they can tell how well the solar panels are going to work, so that they know they're going to get the right energy, and they're going to provide us with basically having the right plugs to plug in for the rest of our instruments. And yet another cool test that spacecraft go through, acoustic test. So this is a big speaker back here. And this room gets closed off, the spacecraft gets built in, they close these huge doors, and they basically blast music at the spacecraft. That is to simulate what happens at launch, when you launch the spacecraft and have it shake. They go through that and make sure that they know that nothing falls off, that nothing is broken, and so that's yet another test it's gone through. So this was one of the last pictures of the spacecraft as it goes through, or just before launch. And I've highlighted here the cup that's standing out from the heat shield. And then we have those other two sensors that are going to go and again sense all that solar wind, all those coronal mass ejections, all those different things that are coming off of the sun. And the panels that you saw tested in the purple, and the phone that we're going to phone home with. And this is on top of the rocket, the Delta IV Heavy, with an extended third stage, an extra boost in this great big fairing here. So the fairing is the outside part of the spacecraft. So that spacecraft was the work of many different people. So you saw some pictures here of only a few of us who worked on the spacecraft. There were actually probably thousands that worked on the spacecraft. These are folks from launch services that I work with, so they help with the Delta IV Heavy and actually putting that together. This is also a group of the scientists who work on this project. And this is actually Gene Parker, the person who the spacecraft is named for. Gene is a real inspiration. He's a really amazing guy. I've gotten the pleasure to work with him a little bit. And he really is a story of perseverance, and a good story, I think, for scientists, good advice for scientists is that when he first published his paper about the wind that we now know, because we've gone and tested it near the Earth, that this wind constantly comes off the sun, folks laughed at him and basically said that this paper that he wrote couldn't work. It just couldn't be possible. And he had to try multiple times in order to get that idea out. And so he went to a trusted advisor or editor and said, I really think that this is okay. And the editor checked the math and said, well, yes, your math is fine. So I'm going to have to allow it because I don't have any other reason besides folks just think it's new or weird that I won't publish it. And so they published his paper, and he ended up not being exactly right, but being very close to right. So he knew that something was there, and within a year or two, the woman here, Marcia Neubauer, actually worked on the experiments sent into space that proved him right. So he's a great story and a great inspiration, and the first person that NASA has ever, living person that NASA has ever given the honor of naming a spacecraft after. And this is my family at launch. My niece and nephew got to come with me, as well as my mom and my dad and my sister and my brother-in-law. The launch was at 3 a.m. So you wake up at around 1 a.m. and you roll out of bed and you get in the rental car and you get to NASA Kennedy, and you're able to go out for the night launch. And I highly, highly recommend a night launch if you at all have the opportunity to do so. And that's Parker in the background under the spotlights back there. And then this is the launch video. I had seen other launches. As I said, I was a rocket scientist, but this one was the scariest one I think I've ever seen. Mainly because of all the fire that you'll start to see in a minute.
-15, pro for your ignition. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
I was sure it was on fire.
Liftoff of the mighty Delta IV Heavy rocket with NASA's Parker Solar Probe, a daring mission to shed light on the mysteries of our closest star, the Sun.
So what's very interesting about this is as you hear the testing that I was talking about, the vibrations, this sound is the exact sound that you hear when the testing is happening at NASA Goddard. Because again, they have the exact profile so that you test that you know you can survive this.
Seconds in. Chamber pressure on the core booster is throttling down to partial thrust mode. Response looks good. 50 seconds into flight. Strap-on boosters look good in the full thrust mode. Core booster looks good in the partial thrust mode. Now 1 minute into flight. Vehicle trajectory looking good, right down the middle of the range track. 1 minute, 10 seconds into flight.
And that was very important.
1 minute, 19 seconds into
right
flight.
down the center of the range, because that means that we have energy to, or gas left in the tank to keep moving well after the nominal mission. Because if we were not in the center, we'd have to correct it by using gas to move the spacecraft.
1 minute, 45 seconds into flight. Trajectory continuing to look good right down the middle of the range track.
And so about now is when you're on the ground is about the last time that you actually see it. So the last time that I saw Parker Solar Probe, she was on her way, and it just she looked kind of like Venus does in the night sky, and then disappeared as she started on her voyage racing towards Venus at that point in time. And so speaking of that, so she left the Earth and raced towards Venus. So by Halloween, she was the fastest. She was on the largest rocket, the man-made rocket of the U.S. arsenal. She was the fastest human-made object, and so she keeps beating her own record every time we go by Venus. So we beat our record in 2018. We beat it in 2019, and we'll beat it again in 2020. As we spiral in closer and closer to the sun, eventually getting to kind of a stable orbit, no more than 10 solar radii from the sun. So this is we're very close in. We went very fast, and again, that Venus trajectory to change us, to push us further in towards the sun each time we do that. We'll do that. We've done it twice, and we'll do it 5 more times before we get to that. So the first closest approach was 35 solar radii away, which is about equivalent to, if you look at the distance from the Earth to the sun as an American football field, that's around 100 yards. We'll eventually get into the sun's 4-yard line. So we'll go 96% of the way to the sun if we're coming from the Earth all the way to the sun. We were about at the 28-yard line for the initial encounter with the sun, and then we'll step in closer. We've already stepped in closer once, and again 5 more times. And so again, we will use Venus. And something unique that we have done is that we're able to take pictures and data around Venus. We were the distance above Venus that is the same distance between Boston and Oklahoma City. So we were very, very close to the surface of Venus. And we are currently planning in July to take pictures as well as to take samples and hopefully learn a little bit about if there's aurora on Venus, if there's what's going on in the atmosphere, and different things like that. So we're not just a solar mission, we're also looking at Venus. And kind of some other interesting things that we've done is that we've looked at out of the solar system towards the galaxy, so towards other stars, and have looked for actually quasars with our white light imager. So we're doing a lot of different science. It's not just the sun. We have such great instruments and such a great instrument team that we're able to do lots of things. And again, it's about the people. This is the moment of closest approach 2019, just a picture of us. We were all out having pizza before closest approach. And before we saw this first image from the telescope. So that was even before we saw the image, we were happy. And then once we saw this image, it was even happier. And as you note, it's not of the sun. The sun is off in this direction. This is actually the Milky Way. So this is our galaxy. Galaxy is a collection of stars, and so our sun is in the Milky Way galaxy, and that's our Milky Way, looking off towards the center of the galaxy. We're kind of on the arm of the galaxy, or the outskirts of this galaxy. So we saw this and just saw this amazing, beautiful picture of in just perfect clarity. Meaning that the instrument works well, and that we'll be able to see the solar wind and kind of striations of solar wind, or these stripes of solar wind that come off, and we're able to study those and really understand that. Another surprise that once we got there was that it's a little dustier than we thought it was going to be. So we also see dust streaks. We see dust hit this in the movie version. I don't, unfortunately, think I put the movie version in here. You see dust come and hit the spacecraft and make a mess. So when you think about dust in your house and how it can kind of form the little dust bunnies, well, this hits the spacecraft and actually causes a spray of basically dust bunny or dust particles off. So there's a lot of interesting things going on in space that we weren't prepared for, didn't quite know that we were going to see. So this is now going to introduce one of the things that we talked about earlier, was to go to the sun to really understand that space weather. So to understand those explosions that come off the sun, to understand how we can better predict them, how often they really occur, when they're going to be directed towards the Earth, when they're not going to be directed towards the Earth, all of those same things. And if you remember back to those videos, you saw huge explosions and huge things coming off of the sun. And so now I'm going to play one of the videos around the time of Parker's first closest approach, so the first time that we went towards the sun. So this is an image not taken by Parker, but taken by another NASA spacecraft, the Stereo Ahead, which is a spacecraft which is a little bit ahead of the Earth, so it could actually see the part of the sun that Parker was doing. And so there was a coronal mass ejection. So again, do you see anything? You really didn't see much in this. And if someone had asked me just to watch this movie and point out a coronal mass ejection, even after looking at these for the last 15 to 20 years, I probably could not have told you exactly where this was. But now what we've done is we've taken one image and subtracted it from the last, so that you could actually get a little sense of the change and see if in the change we can see anything like some of these coronal mass ejections. So I think it's a little more obvious over here that there was an ejection. So I'll play it a few more times. You're starting to see kind of motion flowing through here. And this, again, taking that stereo data and subtracting one from the other so that you see differences. So it helps your eye really see the difference. It's like kind of like the enhance button that some TV shows talk about. So there was this slow eruption over here, still, equivalent to maybe 50 million school buses hurtling at us at 1 million miles an hour, but definitely much smaller and nothing that you would have seen from the Earth or thought of from the Earth. So it was important to understand this, and again, one of our motivators for this whole mission and for going closer was to really understand this, because if this is happening, and this has happened 5 times already, Parker has flown through, at least 5 times, has flown through one of these, we really need to understand that, so that when we go out to the moon and when we go out to Mars and we go out to other places, we have a good, safe space weather report, and we know to keep our astronauts safe, and we know that our spacecraft electronics will work, and also, you know, in the long run, also predict when we can go see aurora, and go and see the beautiful things that it produces as well. So that is what it looks like in the images. And this is what Parker actually, the data it actually takes. So it's not quite as interesting. It's not as big, pretty pictures, but it tells you a lot. So the top is telling you how strong that magnet is. So as it goes up, it's a stronger magnet. This is which direction it is. So like whether your magnet, if you put it on the opposite side, it wouldn't attach to the fridge versus attaching to the fridge, it tells you which direction it's pointing in all of these. That's the two different blue colors here. It tells you which direction the magnetic field is pointing in. This tells you how fast it's going, how fast all that gas was going by you. This tells you how dense it was, how much of that stuff was packed into. Was it thick and dense like a tabletop, or was it more like gas? Or was it like water? How dense was it? And then this is the temperature. And the temperatures actually get cooler because the stuff that is being ejected or being forced out is actually from that cooler, sometimes that cooler region beneath the atmosphere that's coming up along with it and being pushed up and out. So this was the coronal mass ejection, the first one that we flew through. And what was interesting is that when we predicted for Parker, what we thought we would see is we thought we would see maybe one in 7 years, just because of how often we thought they occurred. And we've already seen 5 within the first year and a half. So this means that there's a lot more of these to be found. There's a lot more science and research to do. So me and my hundreds of colleagues have lots of work to do, which I think is just absolutely great about going to someplace like this, especially because this is a simulation of what happens when a coronal mass ejection comes towards the Earth. So this is the Earth, and we're being bombarded by the solar wind, but this dense part over here, a more dense part, is actually the particles that are coming towards the Earth in that coronal mass ejection. And so it becomes like a snowstorm or like a blizzard, kind of whiting out. And it's interacting around the Earth, and the Earth has a protective magnetic field that keeps us, and they're going to show you that drawn out as the magnetic field. But so every once in a while, some of these particles, again, get down into the magnetic field. And as those particles and that gas follow the magnetic field, like a guide, like on a track, like a trolley, it will come down and it will actually cause aurora. So they'll light up and actually cause aurora on near the poles, either the North Pole or the South Pole. So in this, we really do need to understand how this is, how many times we're going to see these, where we're going to see them, because very well, if we have folks going off to the moon, to Mars can be in a different location than the Earth. So if we're all clear at Earth, we might not be all clear at Mars. So how do we start making that? Or what about things we have at Jupiter? If we have spacecraft at Jupiter, we also need to know what the space weather is going to look like there. So it's all important research that we're doing here. So what's next for Parker Solar Probe? So actually this month, in just a week, we're going to release even more data and even more science from what we did. Scientists have to write papers and have to tell folks about what they did, because that's very important to share what we've accomplished. And we did a huge data release in late 2019 in terms of we had some papers in the Nature magazine, as well as then a bunch of scientific articles, over 50 scientific articles. There's more coming April 14th, a week from now. And then May and into early June, we're going to have our 5th encounter with the sun. And we'll turn all our instruments on. We're busily preparing. Just before this, I was on a telecon setting up all the commands for what's going to happen during that encounter, how many times we're going to take pictures, how many times we're going to sample the gas, and what temperatures and what range is. So that was all set up. And then July 11th, just after the 4th of July, we have our third encounter with Venus that will, again, use a gravity assist to push us further in. So we'll have yet another new unexplored territory, and we'll beat our own speed record then in, I think it's mid-August, I think, is when we beat the actual speed record again. So we'll be the fastest human-made object yet again again this summer. So I really hope that you've enjoyed this little foray into learning about the sun, and come and explore with us for the next 5 or 6 years that we're out there exploring the sun and learning more about how to live with a star. So with that, if there's any questions, I'd be more than happy to take some questions or leave it there. Thanks.
I have a question. How can a person find out more after this talk about what you guys are up to there? Is there any sort of a website, or is there anywhere that a person can go and access to sort of keep track of what you guys are up to?
Definitely, definitely. So there are websites. There is the NASA Parker Solar Probe website. There is also the John Hopkins, who built the spacecraft. They have a Parker Solar Probe website as well. Those two are great locations. We have a Twitter feed. It's at The Sweep Life. So SWEAP, not SWEEP. I think we also have an Instagram that we try to update with our stories about what we're doing. So those are kind of great ways, and NASA is very good about sending those out. There's another asset that I really like to watch. It's called DSN Now, so Deep Space Network Now. And it'll show you where the Deep Space Network is connecting to and when it's downloading from Parker. So you see a little dish light up, and it'll look like it's talking to one of the spacecrafts, and it'll tell you a little bit about the spacecraft. So that's kind of fun to see when it's talking to its different, all the different spacecrafts, not just Parker, but all of the different spacecrafts that it talks to.
Any other questions? You can unmute yourself if you'd like, if you have a question. I think that this was great. I do have one more question if no one else is going to jump in. And that is, how did you get involved in this? What made you excited about becoming an astrophysicist?
That's a very good question. So what got me interested and excited was actually very interesting. I've always been excited and interested in math, in science in general, and nature, how things worked. So I took apart my fair share of cameras and various other electronics, much to the chagrin of my parents and grandparents. But astrophysics specifically came late to the game. I was a physicist by training, an undergrad, was trying to decide what to do with that exactly. And I was studying to do kind of more particle physics, very mathematically based. And my friend, I was procrastinating on a problem set, and my friend asked me if I'd wanted to watch a movie. And in these days, you had to you actually had to have a DVD player to have a movie. So we went into a classroom and had a DVD, and she showed me this DVD, and it was these images of the sun from the TRACE satellite. And NASA's TRACE satellite. And so I was just mesmerized that there was all these huge loops there were pictures of, and they were shaking and they were exploding. And I thought that was just such an interesting thing. And I asked her, well, like, how do you get involved? And she was like, well, actually, it's all free. You just have to, you could work with this professor. So I changed professors, started working with that professor on my PhD. Actually, I was about to leave the field about 3 years later after a postdoc, was having just some difficulties finding kind of the next thing. And my mentor told me to take do one more talk, and then we'll figure out how to you know, how to find something else for you to do. And says, all right. So I went and gave my talk, and my current boss walked up to me after that talk and was like, hey, would you like a job building instruments and doing this? And you would work on the TRACE satellite, and you would be the operator for that. So the TRACE satellite really has a lot to do with me being here, being first interested, and then also my first job out of grad school, or after postdoc out of grad school. So after my PhD. So that's kind of how I got interested in specifically solar physics.
Wow, that's pretty cool. And what, thank you for sharing that. That's, it's nice to hear how it all progressed. I have one more question. Can you tell me, do you have any advice for someone who likes math and science, but isn't quite sure where they'd want to go, how they could sort of help navigate themselves?
Well, I would say, you know, follow that and stay interested and stay curious and take classes. And, you know, there are a lot of different ways to kind of be interested in science. So there is being a scientist. It can be a hobby. You know, you can have something like a telescope in your backyard, or you could go and study, you know, and get a PhD in it. But both ways are equally amazing. You know, you can explore museums, you can explore different, you know, try things out, try going to a summer camp or even just an event in the field of interest. So if you're interested in, say botany, like see if there's someplace local, a park that has maybe a talk by a botanist and then talk to them. If you're interested in astrophysics, you know, find an astrophysicist that you can ask. If you know, find someone who's interested in that and talk a little bit more about it and see where it goes.